Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 2nd, 2026, about 4 days ago. It presents a fascinating reality check, finding that spontaneous, aha, moments in reasoning models are actually quite rare, appearing in only about 6% of traces, and usually result in worse accuracy compared to standard reasoning. The paper is titled, "The Illusion of Insight in Reasoning Models." And as we'll see shortly, despite these negative findings for spontaneous shifts, the authors discover that forcing these shifts at the right time can surprisingly boost performance. To clarify what counts as genuine insight, Figure 1 illustrates the anatomy of an aha moment. At the top, we see a simple logic puzzle about ages, asking who is the oldest. Below that, the timeline shows how the model evolves across training checkpoints. Notice that in the first two stages, shown in red, the model consistently fails to solve the problem. However, at checkpoint 3, highlighted in yellow, it generates a pivot phrase, wait, actually, which leads to the correct answer, defining the specific pattern of failure followed by successful self-correction that the authors are hunting for. So Figure 2 formalizes this intuition into a strict mathematical definition, ensuring we distinguish real insights from random noise. On the left, the graph tracks the probability of a correct answer. The criteria require that the model historically fails, keeping the black line low until a sudden spike appears at checkpoint K, where the red dot indicates that a reasoning shift significantly outperforms the average. Then, the graph on the right ensures prior stability. It shows that the frequency of shifts must remain low before this point, proving the model wasn't just randomly changing its mind earlier. Alright, having defined exactly what we are looking for, Table 1 details the specific models and domains used in the experiments. The study tests Qwen 2.5 and Llama 3.1 models across 3 distinct reasoning tasks, cryptic crosswords, math problems, and rush hour puzzles. The columns to the right track the learning progress, comparing accuracy at step 0 against the final training checkpoint. We can see clear gains across the board. For instance, the Llama 3.18b model on math improves by over 8 percentage points. This confirms the baseline training is effective, setting the stage to analyze how that learning happens. Well, now that we see the training worked, Table 2 delivers the first major reality check. The third column, labeled %Sij, reveals that spontaneous reasoning shifts are actually quite rare, appearing in only about 6% of the pooled traces. Crucially, the final 2 columns compare the probability of a correct answer without versus with a shift. If we look at the bottom row for the overall average, accuracy drops from 29% when sticking to the plan, down to just under 7% when a shift occurs. So changing direction usually signals that the model is confused, rather than correcting itself. Okay, deeper than just raw shifts, Figure 4 hunts for the specific formal aha moments, the ones that actually succeed after failure. This heat map displays their prevalence as we adjust the strictness of our definition, with prior failure tolerance on the x-axis and stability thresholds on the y-axis. Even in the most lenient scenario at the top right, these productive insights appear in only about 3% of cases. When we apply stricter criteria in the bottom left, the rate plummets to just over 0.5%, confirming that true self-correction is vanishingly rare. So, given that shifts are generally harmful, Table 4 asks a nuanced question. Could they be useful specifically when the model is highly uncertain? This table splits the data by entropy, separating the top 20% of most uncertain traces from the rest. If we look at the middle section for high entropy, specifically in the math column, the accuracy difference, shown as delta, is still negative 7.4 percentage points. While this is better than the severe 23-point drop seen in the low entropy section at the bottom, it confirms that even when confused, spontaneous pivoting does not reliably save the day. Well, while spontaneous pivoting fails, forcing the model to rethink works surprisingly well. Table 5 shows the results of this forced aha intervention, comparing a standard baseline against a second attempt where the model is explicitly told to reconsider. Focusing on the math column, the performance boost is substantial. Accuracy climbs from about 32% in the first pass to over 40% in the second, yielding a gain of 8.4 percentage points. The win counts at the bottom explain why. The model successfully corrects over 50,000 errors, far outpacing the 23,000 times it backslides. Wrapping up, the big takeaway is that true intrinsic insight in these models appears to be largely an illusion. Spontaneous mid-trace shifts usually signal instability rather than genuine self-correction. However, the success of the intervention suggests we can still improve reliability, not by hoping for magical moments, but by actively monitoring uncertainty and forcing reevaluation when it matters most. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.